All right, part E. Let's see if we can use direct substitution. I look at this function, it's a rational function, and I'm looking at the domain, and I know that we can't have 0 in the denominator here. So I know that if x equals -2, it's going to cause the denominator to be 0. So I know the domain is that it's all numbers except x cannot be -2. And hey, look at this. We're plugging in a x value of -2. So we know that when we have a limit approaching a value that makes the function not continuous, it means we have to use another strategy besides direct substitution. So which strategy do we actually need to use? And that kind of depends on what kind of discontinuity the situation is. So to help me understand this, what I'm going to do is I'm going to rewrite this function by factoring and seeing what happens. So I know if I factor this, it's going to be x minus 3 and x plus 2. In the bottom, I can factor out a 2 and get x plus 2. So now I see that I can create a 1 here by using some algebra, and I know that wherever I can create a 1, that's where what we call a hole, or so I'll just call it a hole for now. And so if there's a hole, to figure out what the y value, to figure out what the limit is, what we'll do is we'll just rewrite this problem without the x plus 2 in there and find that it's x minus 3 over, not -2, x minus 3 over 2, that's all that's left. And then, now that I use algebra to rewrite this form by essentially canceling out those x plus 2's or creating a 1, I can just use direct substitution now and get, when I plug in the -2, I'll get -2 minus 3 over 2, which ends up becoming -5 half. So that's pretty sweet. Some also things to know, that another way to figure out a hole is not just when you are able to cancel or create a 1. Another way to find a hole is if you try plugging in -2 right away in the beginning. When you do quick calculation, you'll find that it ends up becoming 0 over 0. And whenever you attempt to plug in -2 in your head to kind of get a feel what this function is and get 0 over 0, that is also an indicator for a hole. Okay, so moving on to problem, I'm going to skip, I'm going to do F. So F, let's try that same strategy, just trying to plug in. I'm going to do it on the side in my head. Let's see what I get when I plug in 3. So 3 plus 5, 3 squared minus 9, I end up getting 8 over 0. So whenever you get a number over 0, that helps us know that this is a vertical asymptote. Okay? So what I know about, so that helps a lot, because now when I look at what this problem is what it's really asking is what's the limit at vertical asymptote. Now we know that from the definition of a limit, so let me just give an example of a vertical asymptote situation. So we may have a function that looks like this at the vertical asymptote, and let's say this is x equals 3 for our situation. We know that even though the left side limit and the right side limit both go to positive infinity, I don't know for this case, it may or may not, but what I do know is that it doesn't converge to a single number a real number L. Remember, that's part of the definition. And since it doesn't, I know that this any limit, any double-sided limit of a vertical asymptote does not exist. So I don't even need to do any analysis. I already know it doesn't exist because it's a vertical asymptote.